I'm going to demonstrate for you that failure is the greatest superpower in science. And I'm going to start off with an analogy of a young child learning to walk for the first time. The young child does not know how to walk when they're born. They just have to keep doing trial and error, failing, falling on the little butt until they learn how to sequence their little mud flappers in the right order to be able to propel themselves wherever they want to go. Now, the little baby has an advantage over scientists, that the little baby has a template, a guide. In other words, they see their parents walking, so they know what the outcome of their experimentation should look like. They have a guide, they have a template. We do not have that template or guide in science. We don't know what success looks like. We don't know what the theory of the universe looks like. We don't know what experiments to try and fail at in order to determine what the proper model of the universe is, what it should look like, what is the possibilities. Can we go faster than the speed of light? How do we go faster than the speed of light? All of that stuff we don't know. And therefore, because of that, it's going to take a lot more trial and error, because it's going to take a lot more to figure out what we don't know than what we do know, because again, we do not have a template on what the final theory should look like. And if you want an example of a science fiction show, Star Trek, this woman was a human that crash landed on an alien planet, and the aliens had no guide, no template of what a human should look like. And in trying to put her back together, they made all these mistakes. So we should expect that we're going to have similar problems, failures in our stumbling through the dark, trying to figure out what the possibilities are, and we're probably going to end up having loss of life along the way. What complicates this problem is that our footprint in the universe is very tiny. We pretty much, our extent in the universe is the tiny scum layer on the face of the earth. And worse, even worse than that, is the template of the universe within the mathematical universe is this tiny little footprint here. So we're a very, very small portion of this footprint, which is a very small portion of the mathematical footprint. What I'm trying to say here is in mathematics, you can have infinite number of dimensions, even fractional dimensions, but the actual universe is only understood to be around a dozen dimensions. And because our actual footprint of what we know of our extent is insignificantly small compared to the mathematical universe, that we should expect virtually infinite number of mathematical models that could explain everything we know right now because our footprint is so small. I demonstrated this to you in the previous video where I showed an experiment that had 4 different models that explained the results of the experiment exactly, in spite of the fact that each model had a different field phenomenon. To go forward, we're going to have to pop a lot of bubbles. We're going to have to fail these models. Each one of these bubbles here represents a mathematical model that explains everything within our tiny, tiny little footprint. And there's going to be infinite, virtually infinite number of these little models that are going to fit everything we know. Before we go on with popping bubbles, let me introduce this video. This is the 3rd video of Distinti's Rules of Scientific Acquisition, version 5. In this video, we're going to classify the different types of models in order that we can learn how to better pop them. And we're going to demonstrate culling the bubbles through failure. Failure is the only way forward, is what I'm going to show you. The following rules of acquisition are going to be demonstrated in this video. The wrong answer tell, the anomaly tell, the paradox tell, the failure imperative, and reciprocal thinking imperative. Talking about tells for the very first time, what is a tell? A tell is a means to discern something without actually having 100% knowledge of it. For example, all these monkeys are playing poker. And this guy, if he's trying to bluff, he may, have some particular type of twitch, or he's tapping his chips, or he folds his cards in and out. So all of these things can be used by the other players to determine that this person may be bluffing or not bluffing. And that's what the tells of the rules of acquisition are. They're a way to tell that a model is a failure without actually having to see it fail. And that way there we can pop a lot more bubbles. And we'll explain how this is important in a moment. We're going to begin with the wrong answer tell. And the wrong answer tell basically means that we can only actually prove models false. We can only fail models. Okay, going back to Karl Popper, logically no number of positive outcomes at the level of experimental testing can confirm a scientific theory, what we're calling a model, to be true. But a single counterexample, a wrong answer, can show the theory to be false. So the only thing we can prove is a model false. So failure is the only thing that gives us a definitive outcome. It doesn't matter how many times we run an experiment and it agrees with what we know, it's not possible to discern that that is the absolute truth, because like we showed in the bubbles, there's going to be virtually infinite models that are going to give us accurate answers. So what we're looking for is where the models fail. We need to fail the models so that the ones remaining are more likely to be the truth. And so failure is our only way forward. Confirming theories does not help us. We don't learn anything new by confirming a theory, because there could be infinite theories. And confirming them doesn't help us weed down to the ones that are possibly the truth. And so the formal wrong answer tell is obtaining wrong answers is the most absolute way to fail a model. A wrong answer represents a strong tell, and we'll explain that in a moment, and failure of any tell eliminates a model from the pool of postulates. What's a postulant? Is a scientific model with no known failures that is potentially a true model. This is a ethereal mechanics definition. And I'll show you why we have to introduce this. So understand that a postulant is basically a contender for a theory of everything. And like we said in the previous video, we can never accept that we know the truth. So we can never call anything a true model, but we can call them as a postulant. It's a contender for the truth. And we should expect that we should have multiple postulant models sometime in the future. And so 2.0, a single counterexample fails a model. And again, we're using the term model to represent models that have a theory or don't have a theory. So what we're going to do now is we're going to introduce the tells punch list. In this punch list, we have some assorted models. This is classical stuff, classical electrodynamics split out by the submodels, and this is ethereal mechanics. And we demonstrated in the past video that it took over 2,000 years for us to find the counterexample to Archimedes' principle. And because of that, it now has a wrong answer, and we can now put under rule of acquisition 2, which is a wrong answer, tell a failure. And down here, we have a failure for the Biot-Savart as interpreted by Heaviside, and also for new electromagnetism V3. If you want details on these failures, you go to the previous video. We're filling this out now for the first time. So there's up to 18 different tells over here, and this is their rule of acquisition number at the top. And when we put the codes in here, it'll light it up. Now over here, this represents the overall score. Failures are automatically a failure for the model. Okay, an anomaly tell, which we're going to get into next, the anomaly tell is a conditional tell. It may or may not fail a model, and we'll get into that more. So this is how this tells, and we're going to every time we introduce a new tell, we're going to fill out this according to what the tells tell about these models. So now the drawback of the wrong answer tell, as demonstrated by Archimedes' principle, is that it requires us to have a counterexample, a wrong answer. Now within our limited footprint, all of these models here are essentially going to give us the correct answers for everything inside of our footprint. And like Archimedes' principle, we had to extend our footprint by advancing propulsion technology. It took 2,000 years after Archimedes' principle was developed to get ships' propulsion technology to the point that ships could go fast enough that the phenomenon of squatting could be encountered. And then we could have our counterexample and cross off one of the bubbles, to pop one of the bubbles. And that is the drawback of the wrong answer tell, because it may take hundreds to thousands of years before the technology comes available to encounter the counterexample. And it might even be the case that we're stuck in one model. We believe maybe that there's only one model, and this model may not offer us a technological advancement that will get us to the counterexample. That is what's happening now. We're stuck in one set of models in legacy theory, and those models have been stagnant for over 100 years. We're going to talk more about that in a moment. So the important point to take away from this is because the wrong answer tell takes a long time, it may take hundreds to thousands of years before we find the counterexamples, that we need other tells to allow us to fail a model without necessarily having a counterexample. These are like the tells we described in the monkey example. In other words, you can tell if your opponent has a good hand or not without actually having to see the hand. That is the purpose of the other tells. The red tells are hard tells. There are strong tells. There are 14 of them. Violation of a strong tell is an automatic failure for a model. Like, for example, a model cannot have a paradox. If a model expresses a paradox, the model has got to be popped, gone, either improved, fixed, corrected, whatever. But once you change it, it's a different model. It's a different bubble. The blue is a conditional tell. We're going to explain that later. A conditional tell might be a hard tell under certain conditions, but it may not be a tell under other conditions. We're going to talk about that. That's the anomaly tell. The three over here are weak tells. These are not necessarily concrete indications of failure. And the example is the oldest expression, red sky in morning, sailor take warning. Seeing a red sky in the morning when you're at sea is not a 100% indicator that you're going to experience a storm problem. But it's something that you should now be warned to keep your eye on. Okay, when we get a theory of everything, I should have called this a model of everything. The model of everything cannot violate any tell. So in the end, if your model of everything has a weak tell, you have to justify it and say that these weak tells are not a problem for this guy, and it has to be justified. And so our problem today is we can't expand our footprint because legacy science thinks that everything we know only is one bubble. They believe that they have uniqueness. They believe that legacy electromagnetism, quantum mechanics, and relativity are everything that's ever possibly needed, and there can never be anything else. They believe in their own silliness of uniqueness, so they only believe in one bubble. And these three items are sub-bubbles in here, but the problem is they don't talk to each other. They don't unify. This is not really a complete bubble. These are like separate bubbles. We have a problem. We can't go forward with these. They've been stagnant for over 100 years. And scientists will not accept a lot of the counterexamples. And we're going to use the tells to show you that these guys are a popped bubble, and we need to get rid of them, pass them as quickly as possible, and go out and find another bubble that's going to give us more success in expanding our footprint. And so that you understand that I'm not just making this up. There's a lot of videos out there. Just look up Cosmology Crisis, and she says it's getting worse. That's not really the case. The point is your models haven't been able to predict anything in 100 years. So the crisis has been there since the beginning. It's only now you're reconciling that we're never going to get anywhere with it. We've been trying for 100 years, and what we've been publishing is essentially garbage. Because scientists do not want to admit that they're wrong. They do not want to admit to failure. And so they're coming up with any reason to keep these garbage old theories alive. And we're going to get more into that as we go along. The important part of this is extinction level events are always on their way. Always. Go ask the dinosaurs. They did nothing about it, and they got boomed by an asteroid. And we have all of our eggs on one planet. One asteroid impact, one supervolcano, one mega I said supervolcano, one nuclear war, one major plague. We're all dead. We need to get people off the planet in significant numbers, not just to save the human race, but to save the ecosystem of the Earth, because the Earth isn't getting any bigger. So let's get on to the next tell. This is the anomaly tell. The anomaly tell is a conditional tell. And what's the definition of anomaly? Again, this is a definition that is specific to ethereal mechanics. You will not see this in a normal dictionary. This is a definition we're using. It's close to the word anomaly, but there's little slight differences. So an anomaly in our new science paradigm is a mismatch in causes and or effects. You can read the rest of this on your own. So in other words, you can have a model that fails to predict an observed effect or phenomenon. Like, for example, you have relativity that cannot predict why spiral galaxies are spiral or they're winding. Okay, you can have extra effects. A model predicts effects that have not yet been observed and cannot be reconciled. Okay, and we have one of those in electromagnetism, a new electromagnetism, and we'll talk about that in a moment. And there might be missing causes. The model requires other inputs like dark matter or another derivational step in order to properly predict observed events. Now, the reason why these are not hard anomalies, not hard tells, is because the missing effect might be the fact that this particular effect is not supposed to be accounted for by this particular model, may be accounted for by a different model. The extra effects may be the fact that we don't have the technological footprint right now to be able to observe these things. Like maybe dark matter is there, we just don't know how to observe it yet. And yada, yada, yada. And so that's why anomalies are not hard tells. And anomalies, though anomalies must be reconciled. And an example of anomalies is the Earth-centric model from Galileo's time. So prior to Galileo doing his work, humanity believed that all the stars and all the objects in the sky rotate around the Earth. This is called the Earth-centric model, meaning the Earth is the center of the universe. And this model predicted very accurately the positions of 99% of the things in the night sky. What it didn't predict are these 5 anomalous things that wandered the night sky and decided not to fit into the model. And the Latin word for wanderer is planet. And so what Galileo did is he expanded the footprint of our technology to improve the measurement of the motion of the planets so he could show that these planets were revolving around the sun and that we were too. So this is the first case of showing where science got things backwards. Well, it's not the first case, but it's one of the cases to show where science gets stuff backwards. We're not the center of the universe. We're far from it. And this theme of this video is I'm going to show a lot of things that we got backwards. So the 8th rule of acquisition is the anomaly tell. Anomalies are seeds that can, not will, but can grow into great oaks from whose branches we can see farther. Warning, anomalies can be the harbinger of catastrophic change, as demonstrated in the Galileo. Those 5 objects out of thousands that are in the night sky. You want to ignore them because they're tiny anomalies, but when you finally account for them, it may require you to completely flip upside down what you believe about nature. Okay, size does not matter. Ultimately, a theory of everything is not allowed to have any anomalies. You have to resolve all the anomalies before you can get there. Again, we're going to be going into postulant models. So we're never going to accept the truth that we know the truth. This is a diagram in an attempt to kind of organize all the concepts of models. So we have empirical models, which are models that have no mechanism. Fantasy models, which do have a mechanism, but the mechanism is known to be false. In other words, it's a mechanism it's not the mechanism by which nature does something. Okay, an example of that is we can say that the Earth-centric model is a fantasy model because we still use it in navigation. We still say in navigation that the sun rises in the east and it settles in the west. And even though that's a false model, it's still useful. So we can still use it, but we know because it violates the rules of acquisition and it's not the correct model, it does get the right answer for most objects. So therefore, we can still use it. We can still use fantasy models even though their mechanisms aren't true. And then we have the anomalous models. The anomalous models are those models that only have anomalies or weak tells. These are the models that we're developing to one day become postulant models. Postulant models have no violations of the rules of acquisition, and they get correct answers. That's why they're here. They are basically the candidates for the truth, but we're never going to allow ourselves to believe they're true. We're going to continue to test them and try to fail them for the rest of humanity's existence. That is the safest thing to do. This was talked about in the last video. If, in fact, we have a postulant model and one day we find a counterexample where it's wrong, it slides down to this location here. If it hits an X, it slides until it hits a box. So whenever you have a wrong answer, everything always slides back to the wrong model. Wrong models are not useful because they give wrong answers. Okay, so on this dimension here, we have the accuracy of the model. We have correct models that give correct answers, conditional models that get correct answers under certain conditions, approximations, and then we have wrong models. Okay, the items in this area here are allowed to violate any tell except tells 2 and 9, because tells 2 and 9 drop it down to the wrong answer box. So fantasy models and empirical models can violate any of the tells except 2 and 9. Anomalous models can only violate these tells right here, 8, 21, 22, and 23, the weak or conditional tells. Okay, to advance to postulant, you have to have no violations of the rules of acquisition at all, and you have to explain anything without any wrong answers within our ability to measure. What typically happens is our ability to measure improves as our technology improves, and that may show wrong answers as we show that our tools of measurement become more accurate. Just like Galileo improved the measurement accuracy so that he could prove the Earth-centric model wrong. Now that we know what anomalies are, we are going to apply them to our punch list now. Everything here in blue provides an anomaly, and you can see it bubbles out to the left. The standard model has an anomaly because it can't predict gravity. That's a mismatch. I forgot what special relativity's anomaly is. When I remember it, I'll tell you. General relativity has dark matter required to predict the stars, so that's its anomaly. Quantum mechanics, according to their own Brian Greene, cannot predict anything in the real world, so they haven't been able to reconcile that anomaly yet. They're working on it. Okay, in classical electrodynamics, the only thing we can say right now that Faraday's law has an anomaly because it can't explain the inductance of a straight piece of wire, and we know a straight piece of wire has inductance because dipoles, antennas, have inductance. And we're going to have a video out there that shows, in fact, that Faraday's law and these guys are all actually wrong. That would be the latex experiment, but we'll fill that out later when we get to the latex experiment. Ethereal mechanics has anomalies all the way down the line. We love our anomalies because our anomalies tell us that we have more to go. The rabbit hole, we're not at the bottom of the rabbit hole yet. So we're not embarrassed by anomalies. Science should not be embarrassed by failures or anomalies. These are the indicators we're not done. Okay, these are important for us. And in ethereal mechanics, we relish our anomalies. In fact, instead of me listing them, I'm going to produce a separate video to go over the current anomalies in ethereal mechanics. Therefore, every time we improve it, we'll issue a new version of this. We'll change them. That way we won't have to keep changing the rules of acquisition when the ethereal mechanics anomalies change. So we're going to have a separate video series which are going to detail all of the presently known anomalies of ethereal mechanics. And the reason why failure is wonderful is because this is what Niels Bohr said, and I agree with this 100%. How wonderful that we have met with a paradox. Now, this could be a wrong answer, a paradox, an anomaly, a violation of the rules of acquisition. Doesn't matter. Now we have a hope of making some progress. Failure is the way forward. A paradox is actually one of our rules of acquisition. And we have, again, our definition of a paradox in ethereal mechanics is a contradiction of the models or applications thereof. See, a wrong answer is a disconnect between the theory and nature. An anomaly is a disconnect between the causality and nature. And a paradox is a contradiction or a disconnect among the models themselves or the applications of the models. An example is the ladder paradox, which is special relativity, and the time traveler paradox, which is also special relativity. And you can look these up. Basically, the time traveler paradox is you go back in time and kill your grandfather, and then the paradox is, well, then how are you born? Okay, and the paradox and this is Ayn Rand's definition of why a contradiction cannot occur. The ninth rule of acquisition is a paradox indicates a corrupt model or an application of a model. The ninth rule of acquisition is a hard tell, and a theory of everything cannot be paradoxical. So let's apply this to our punch list. So special relativity has the ladder paradox and zombie mechanics. Now, zombie mechanics is quantum mechanics after they buried Schrodinger's cat in the pet cemetery and got something that's both alive and dead at the same time, aka a zombie. So this is quantum mechanics where they use superposition. This is quantum mechanics where they use distribution, probability distribution. And the reason why zombie mechanics fails is because of these paradoxes here. I looked up on AI and said, what are the paradoxes? And these are all related to Schrodinger's cat and the Einstein-Podolsky-Rosen paradox, which is basically entangled particles, which both of these are zombie mechanics here. There are no violations of any of this stuff here because these are the last boxes we will check as we go to the right on this table and check off all the boxes. You can see how this table works. Because this failure supersedes an anomaly, then that wraps this guy up to the overall of failure. That's what these are. These are the status of these models on the left. As we go more down the list and go to other videos and we keep filling out the punch list, you're going to see all of these turn red. Possibly, yeah, even this guy will turn red. There's going to be no other violations of the rule of ethereal mechanics at this point because ethereal mechanics was developed under the rules of acquisition. And every time we hit one of those things, we stopped and we improved the model. That's why we're up to new electromagnetism V5. And if we ever fail, we go to new electromagnetism V6. We just keep going to the next bubble, baby. The next bubble. We keep popping the bubbles as we go. It is not a thing to be feared. That's the only way forward, is just to keep applying the models and finding the anomalies and going forward. And as we keep expanding our footprint, we're going to keep popping the bubbles. And somewhere in this field of infinite bubbles here, there is the right answer. There is the truth. But because our footprint is small, we're going to be narrowing down every time we keep expanding our footprint. All we're going to be doing is narrowing the number of bubbles. Theoretically, we should never be able to get to one bubble because we will never have an infinite enough footprint. Okay, and that is why the tells and the rules of acquisition will help us pare down some of the ones that we can't pare down because of the large footprint. And this is why we have the failure imperative, because we don't have a roadmap or example of what is ultimately possible. Just like the little girl learning to walk, unlike the girl learning to walk, where she has the example of what she is striving for, of what she is trial and erroring for, we don't have that. And because of that, it's going to take a lot of fumbling around in the dark. And we should expect to fail a lot. So we should start embracing the failure. In fact, we should start celebrating the failure. In fact, all of our experiments should have that the preferred outcome is the experiment fails to confirm a theory. That we should design the experiments with the intent of failing the experiments. Because failure is the only way forward. And here's Niels Bohr again, where I've left it like a Mad Lib. How wonderful we had met with fill in the blank. Now we have some hope of making progress. This is the failure imperative, the 26th rule of acquisition. Okay, but we scientists have it backwards. Scientists are worried about credibility of failing. You know, but science has it backwards. Like we have a lot of things backwards. Scientists are worried about failing, what it does to the credibility. Experimental failure is looked upon as a mistake, a sign of professional incompetence, something to be avoided because it adversely affects funding, promotion, and reputation. Because of this, experimental failures are hidden and downplayed. Experimental data is cooked to spin a win of some kind, to spin a positive outcome. And because of that, science has been corrupt. Look at Gravity Probe B. I asked, is Gravity Probe B successful? And AI said back, oh yeah, it was successfully launched. But then they just gave gibberish of what it was supposed to do. Everything I've looked at for Gravity Probe B, I'm sure you've all never heard of it because it was a big fanfare until they got the data back and they couldn't figure out what to do with the data. Okay, I'm sure there's a lot of cooked papers out there that says, oh yeah, it confirmed this and it confirmed, this. But as far as I know, it was a failure. But you won't hear of it. And the cracks are starting to form in science. Sabine has released a paper, a letter that she got over 7 years ago, that's confirming that pretty much everything in science is garbage. And I'm going to put the link in the low bar to this. Watch it on your own, but at 35 seconds in, basically what is published in the Foundation of Physics is nonsense and continues to be nonsense. We've had over 100 years of going nowhere with this nonsense because we have everything upside down. Instead of celebrating failure and going toward failure, we are fearing and shying away from failure. This is the backwards way to do science. So we need to turn science upside down. We need to design our experiments to intentionally fail the existing theories and models, to intentionally destroy them. We should not be putting all these theories up on pedestals and holding on to them for hundreds of years. And because failure is the intended goal, that is the winning outcome. We can start popping the bubbles, and there's no need to hide the failure because that's the intended outcome. And because we should never accept that what we know is the truth, scientists could never work themselves out of a job. Think about this. If scientists believe they've found the ultimate true theory of the universe, well, their job is done. They're out of work. But if you go with this new science paradigm that I propose, we should never accept we know the truth. And therefore, the job of scientists is preserved for life because every year they should start making a new experiment to try to disprove what we believe to be the truth. And if they fail to disprove it, well, okay, they try again and keep trying. Because then every time they can't prove it, just adds one more little notch that maybe it's the truth, even though we can never accept it to be the truth. So that what I am proposing will keep physicists employed for forever and ever and ever and ever, and they will never be able to work themselves out of a job, unlike the present paradigm of science. You see where I'm trying to go with it? You see what I'm putting down here? And therefore, we should actually have holidays when we prove our theories wrong. Like when Maxwell's equation and quantum mechanics and relativity is finally proven wrong and buried in the ground. That should be a national holiday. Because then we can finally move forward with something that will unify the laws of physics. Instead of dragging us back and holding us back. Because like I've said before, our extinction event is coming. It's just a matter of time. It's not a matter of if. And we should have national holidays and parades, and we should have awards for people that are able to find the flaws and pop all these bubbles. Again, we got to pop as many bubbles as we can, as fast as we can, so that the few remaining ones, maybe they're not the truth, but at least they're going to be a lot more useful than the garbage we've been holding on to for 100 years. Again, because science is upside down, I'm going to show you examples where we've had theories upside down, and we need to invert them to get things correct. So the reciprocal thinking imperative is always consider reciprocal causality. In other words, if we say that, like for example, if we say that carbon dioxide causes global warming, we should also consider that is there the possibility that global warming causes carbon dioxide? Or maybe both of those are going on simultaneously. They're only putting out one side of the story, and they're not even testing another theory here. And so there's a lot of things in science we got backwards before we got it right. And I have 20 items on my list. Perhaps one day I'll make a video of all 20. but we're short on time, so I'm just going to show a couple. And the first one is the Earth centrism model I showed you before. We had it backward. Earth wasn't the center of the universe. And then you have the extramission theory that back in the old days, they thought vision was vision beams coming from your eyes and touching things. Okay? But that's backwards. It's not beams coming from your eyes, it's beams going into your eyes. Again, we get things backwards. And then you have the spontaneous generation theory. People in the old days thought that rotting meat produced bacteria and maggots. And they got it backwards. It's bacteria that causes the rot in the meat. And that was proven by Louis Pasteur as late as 1859. Again, we have stuff backwards. We even have, and the science paradigm that we're using now was from this period where we had things backwards. And I put on Google AI, I said, list theories that science got backwards. You can go through and read these on your own or put this in. I love this one, luminiferous ether. Theory popular in the 19th century proposed that a medium called the luminiferous ether filled space carried light waves, but it was disproven by the Michelson-Morley experiment. And Einstein's work. Both of these are false. Both of these are false. The Michelson-Morley experiment, because of length contraction, the best you can say is that the Michelson-Morley experiment couldn't detect the ether one way or the other because of length contraction. So this is wrong. Einstein is complete bullshit here because he said that the static medium is wrong, and he caused the physicists to shy away from it because they weren't getting anywhere with it. And then later on, Einstein introduced the fabric of space-time, which is, by all intents and purposes, a static medium. So all he did was get everybody to put down what they were working on and introduce his own static medium and got them to buy into it. We're still working with a static medium. In ethereal mechanics, we have a dynamic medium which solves all the problems, solves all of the issues that they can't solve with general relativity with their static medium, the fabric of space-time. So, but we'll talk about that. That's not really the focus here. So what did we learn in this video? Second rule, 2.0, a single counterexample fails in model. 8.0, anomalies are seeds that can grow into great oaks from whose branches we can see further. 8.1, warning, anomalies can be the harbinger of catastrophic change. Size does not matter. 8.2, anomalies are not allowed in a theory of everything. 9.0, a paradox indicates a corrupt model or application of a model. 9.1, a theory of everything cannot contain a paradox. 26.0, failure is the only way forward. 29, always consider reciprocal causality and logic. And 29.1, humans usually get stuff backwards before they get it right. If you want to help out, please become a Patreon member. For $5 a month, you can see all the technology-related videos at least a month before the rest of the world sees them. Sometimes the videos I have, I never release to the rest of the world. There's a lot of those too. And it would help me because if I can get rid of my JOB is my #1 source of funding. If I can get enough Patreon members, I can do this full time and I can do more videos faster, even help people to make my videos better. This is the repository. I will explain in a moment how you navigate this. This is the YouTube site that we release all of our new material on. The intro video for this explains how to navigate the repository site. This is our blog site. Big shout out to Sebastian for taking care of this. Again, if I can get the time by having more Patreon support so I can do this full time, I would be happy to spend more time here. Right now, I have spent every vacation, all my vacation time, every bit of free time, except little time at the holidays for family, working on ethereal mechanics. I virtually have no free time left after this. So, thank you. No more voodoo physics. Oh, please like and subscribe.